Hi, this is Jason Gorman from Codemanship. A short apology that I'm not able to join you at Craft Conference in Budapest. The gods have conspired against us and I'm unfortunately not able to be there. So what I thought I'd do is I'd record a screencast of my presentation for those of you who are interested in coming along to it, all six of you, so you can get a taste of what it was about. Before I do that, just a quick plug for my own services. If you're interested in training in the technical practices of extreme programming and agile development, then please check out codemanship.com or codemanship.co.uk, which lists training courses that I offer in these particular areas. Now we've got the nasty business of promoting out of the way. Let's talk about the presentation that I was due to be giving today at CraftConf. Okay, continuous inspection. So if you're interested in doing continuous delivery, and I really think you should be, then one of the key practices within continuous delivery is continuous testing. That is, we're continuously testing and retesting our code to make sure that it always works, that it's always in a shippable state. Going beyond that, though, there's another thing that we need to think about, which is not just whether or not the code works, but also whether or not the code is maintainable. Could it be changed? So we need to be worrying not just about continuous testing, but also about clean code. And for that, what we find is that we need another kind of continuous testing aimed at testing our code to see whether or not it's clean. This is important because we want to be able to sustain the pace of development for as long as we need to, and therefore the code needs to be open to change. Most teams that do TDD don't pay enough attention to code quality, and therefore we tend to find that the pace of development does slow. And therefore, in order to maintain that pace for longer, more effort and more time needs to be put into testing our code to make sure that it is clean. Continuous inspection is very frequent inspection of our software to provide early warning of maintainability and other code quality issues. So it's just like functional testing or continuous functional testing, where we want to know if we've broken the code as quickly as possible so we can fix it cheaply and quickly and immediately. Same thing with the non-functional stuff. We want to know if we've introduced a code smell like feature envy or a long method or a large class. Better to find out as soon as we've done it so that we can fix it there and then. Traditional approaches to code inspections that you may be familiar with or have experience of are things like code reviews, and we'll talk a little bit about these in a second. Pair programming, which is very popular in agile software development and highly recommended, and something that most teams currently don't do, but it's beginning to become more mainstream. Automated code inspections. That's what we'll be talking about for the remainder of this presentation. So the problem with code reviews is, number one, how often they happen. So as with any kind of testing, the less frequently we do it, the more it becomes like shutting the stable door after the horse has bolted. We're flagging up lots and lots of issues that are built up over time, and quite often what we discover is there isn't time to fix those issues because we're already moving on. We can't go back. So for that reason, I'm not a big fan of relying on code reviews in order to actually keep code clean. Having said that, they do have their uses. A code review, if you shift the emphasis from actually reviewing the code to getting the team together to talk about and agree on what we mean by good quality code and what we mean by bad quality code, can be a very valuable thing. So those kinds of code reviews, I think, are a very valuable thing, but they would happen relatively infrequently. Pair programming, as I said, highly recommended. As an approach to code quality, though, as an approach to sort of continuous code inspection, it does have its weaknesses. And the main weakness is it's a human activity, and therefore it's error prone, and we get distracted very easily. Programmers working in pairs or individually have 101 other things to think about as well as code quality. And because of this, code quality issues can easily slip through that net. And so what I've discovered from examining historical code bases for several dozen teams is that the teams that rely mostly on pair programming to ensure code quality don't have code. They don't end up with code that is, in their opinion, clean enough, maintainable enough. And therefore, pair programming by itself, very, very good idea to do it, but it's not sufficient for clean code. So that brings us to automated inspections. If we actually wanted to inspect our code every few minutes rather than every few days or every few weeks or even every few months, then really what we're talking about here is doing it using some kind of program that inspects the code for us. Same principle as automated tests. The more often we want to do it and the more quickly we have to do it, the more important it is to automate that particular work if we can. So here's an example of an automated continuous inspection process. We work on our code changes, maybe we're implementing a user story or fixing a bug or whatever it is we're doing. And while we're doing that, we're continuously running the inspections to make sure that we're keeping the code as clean as it needs to be. Before we commit our code into source control, it's a very good idea to do what we call a clean code check-in. So as well as running your functional test to make sure that what you're checking in will work, we run the non-functional test to make sure that what we're checking in is clean code. We check it in, and then we run code quality checks on the build server as well, as a sort of last line of defense. This is particularly important when you're working with distributed teams, or if you're working on open source software. As a last line of defense, as part of the build process itself, we run a code quality check. If your code quality check takes quite a long time, you might want to consider having some kind of smoke test for code quality. So run a subset of code quality checks on the build server just to be sure, just the most important stuff. If that inspection throws up any issues, it might be that, for example, you fail the build and you throw it back to the developer who committed that code and say, look, you need to fix these issues. The process of actually automating the inspection process is agile software development. You start with a requirement, you agree some executable acceptance tests, some examples of code quality problems or code that has problems and code that we agree doesn't have the same problem. And then we implement our quality gate using code, probably, in a test-driven way, integrate that into the continuous delivery cycle once we're satisfied that it works. And then, most importantly, we feedback and we iterate this design process. So we never get it right first time. We might, for example, think, we've come up with a check for long methods, but it's throwing up some false positives for generated code, auto-generated code. So maybe we need to make the check a little smarter to be able to detect whether it's generated code or not, and ignore it if it is. So we feed that back in and we evolve our code quality checks as time goes on. The kind of quality gates that we would implement in our builds can vary, but there are two general types. A soft gate is one that doesn't break the build if there's a problem. It just reports the problem to make sure the developer is aware and gives them an opportunity to fix it. Having said that, with soft gates, one of the issues with those can be that when I've seen teams use only soft gates, a whole bunch of critical issues in code quality can get through, because there'll be some developers who'll throw their hands up and go, well, I don't really care. Because let's face it, some developers don't. I don't really care, and so everything gets through. So you might want to consider also implementing some hard gates. These are gates that will actually fail the build. They'll break the build if issues are reported. And we can mix and match depending on what kind of quality requirement it is. So let's say, for example, we all agree that a method that's longer than 20 lines of code is too long. Therefore, any method that fails that check breaks the build, and that has to be fixed. Okay, so here's an example of a code quality requirement. Feature envy, that's the name of our code quality story here. And this has been written by me. I'm a developer on the team. As a developer, I need to know about any methods that have more than one dependency on features of another class, so I can move them to where they belong and reduce coupling. So that's my story, and what we do is we sit down, the pair that are going to work on this, and we agree some acceptance tests with the person that wrote the story. In this case, it's me. So I'm saying that this first example here, this summary property get method in C#, is an example of feature envy because there's multiple feature references to address here. The second one we believe is not feature envy. There is a method called to customer, but it's only the one feature that's being used, so it's not feature envy. And the one at the bottom, we have got multiple feature uses, but they're features of this particular object. And therefore, it's also not feature envy. So we would exclude those two last ones and report the first one. Okay. Now, when it comes to actually implementing our quality gates, there are a lot of choices. The bottom line is what you need is a model of the code that contains the information required to ask the question you want to ask. So if the information is about duplication, it could be something that's produced by a tool like Simian. If it's information about dependencies in the code, it could be something produced by a tool like Ndepend, for example. So the tool you use for a particular quality gate will depend on the question you want to ask and what's available and so on. When we implement the quality gate, it's TDD. If you want it to be TDD, it can be TDD. We pick one example, one test case. We maybe have a discussion as a team about it. We implement just enough code in our quality check to satisfy that particular example, and then we test it, and then we feed that back in. Now, exploratory testing comes in here as well. So it may be that we thought of a bunch of examples, code examples for feature envy, but there may be an example that we didn't think of. And so it's important to also apply that rule to other code, apart from the test examples, to apply it to other code and other examples and see what it does, whether we think it should flag it up or whether we think it shouldn't flag it up. So for example, here's one I dreamt up in my head. Is this an example of feature envy? But technically, if we believe that a constructor is a feature of an object or a class, then yes, this is by my definition, this is feature envy because we're using the constructor and we're using the title feature. Now, what I'm saying here in my illustration is we got together as a team, we discussed it, and we decided that we're not going to include constructors. So our current implementation will flag this up as feature envy, and we believe that it shouldn't. So we feed that back in and we adapt and evolve the rule so that this particular example will no longer be reported as feature envy. When are we done? Well, in all test-driven development, the point at which we're done for the time being, until we get feedback from end users and customers, the point at which we're done is the point at which we can't think of any more failing tests. We can't think of any more code examples that our current implementation would not satisfy. Okay. Once we've got it working to our satisfaction, we need to integrate our check into a quality gate, and that means making it part of the build cycle. So going beyond the code now, we're now talking about what the team does in response to a quality check. So if, for example, our feature envy is reported, what should we as a team do? We have to agree a policy for a particular example to illustrate it. So we take our first example and say, look, we think this is feature envy. When it's reported in the build, what should we do? We decide as a team, in this case, that we're going to fail the build. So that's our policy. We implement that in the build step, and we'll show how we do that in a second. And then, very importantly, we test that policy on real code and see what we learn from it. Let's say, for example, we discover that the build is constantly failing because of our implementation of the quality gate for feature envy, and therefore maybe we need to make it a soft gate instead of a hard gate, and things like that. So we learn from applying it to real software, and then we feed back that back into the policies, into the process. So let's say we're implementing our feature envy quality gate using the freely available FXCOP tool that comes with Visual Studio. A simple process for doing that might be to just get check the source code out from version control, compile it, and run the functional unit tests. Very important, this. Run the functional unit test to make sure the code works. Not much point in asking whether the code is clean if the code doesn't work. So check that it works. If it doesn't work, we'll fail the build. If it does work, then what we do is we then apply FXCOP analysis using our custom rule set to the compiled code. And in this particular example, it's going to spit out a full report of all of the issues that it finds. And I'm going to use an XML diff tool to compare the new analysis report to the last analysis report and see what's changed. In other words, what new issues have been reported. Now, FXCOP actually does have an option if you use their FXCOP project tool to have FXCOP actually do that, to only report new issues. But just to illustrate that if you're working with a tool that doesn't have that option, or if you've written all yourself, using a parser generator or something, then what you could do is use something like a diff tool, a file diff tool or an XML diff tool, and do it that way if you have to. So that's why I've done that here. And finally, we look at the results of that. We look inside the diff file, and I've decided what to implement that inside an NUnit test, so that if I find any new issues, I can actually fail the test and therefore fail the build. So there's a kind of a Heath Robinson implementation of a bunch of FX cop rules for a .NET project. Now, as with all practices, you can do it well or you can do it badly. You can be doing all of the technical things I've just described, but still not be succeeding with it. There are some good habits you might want to try and get into. So let's talk a little bit about continuous inspection patterns that can help to make you more effective and to do it more sustainably. Okay, the first one is our house, our rules. Now, this is a fairly straightforward, common sense one. If you get a tool off the shelf, like FX Cop, that comes with a bunch of predefined, pre-rolled rules, if you like, about code quality, you might not agree with all of them. You might not agree with most of them. Let's say, for example, the tool has a rule built into it that says methods should be static by default. Now, I happen to completely disagree with that. I think methods should be instanced by default. And if you want to know why, then just email me and I'll tell you. So I disagree with that rule. I disagree with many rules that come with many tools. And therefore, I find it easier and quicker to just start with a blank slate and come up with new rules. Now, it's very important that you do this as a team. Don't impose rules on people for the same reason that you don't want the tool to impose rules on you because you might disagree with them. You don't want, say, for example, an architect or a technical design authority or a team lead to do it. Don't make it someone's job to dream up the code quality rules. Get together, look at real code, have real conversations, have the debates, have the arguments. And this is when code reviews can be really useful things. Because what we learn in a code review is not necessarily what issues are in our code that we need to fix because they probably won't get fixed. But what do we consider to be issues in our code? What do we agree is good code? What do we agree is bad code? So they're a great forum for doing that. If you're into mob programming, then that's a similar kind of thing. Get everyone in a room, work on some real code, and have those conversations about how long is too long for a method, what is feature envy, and so on and so forth. Get everyone involved and come up with a small set of rules. Hundreds of rules can be very difficult to manage, and you can end up with a quality gate that it's almost impossible to get code through. And you've also got to maintain all of those rules and manage them. So I tend to find a dozen or so rules tends to be about the max that you can live with. So make them the ones that you really care about, and make them so that they are good rule checks. That is, they throw up results that you agree with most of the time. Code analysis code is code. This is about eating your own dog food. The code that we write to test that our code is clean needs to be clean code so that we can maintain and evolve and adapt that as well, so that we can learn about maintaining code quality. If we let the quality of our code quality analysis code slide, and this is not something you can say after a few drinks, if you let it slide over time and it becomes harder and harder to work with, you will eventually end up with a situation where you either live with the rules forever, even though you don't agree with them anymore, in which case they kind of lose their value, or development starts to slow down because you're spending more and more time trying to evolve and move forward your code quality gates. So what can be useful here is bootstrapping. Once you've written a code quality gate in, say, FX Cop with C#, you can actually apply that to the code for the code quality gate. You can bootstrap it, you can turn it on itself, and we'll show you that in a minute. Differential inspections we've talked about. It is a good idea to have your attention drawn to new issues when you do code analysis, but also try on a regular basis to just do a full report, look for all of the issues, just to remind yourself, if you're letting stuff through, just to keep reminding yourself that there's technical debt that you've allowed through, and don't lose sight of that fact. Right, clean code checking we've talked about, but the basic idea is that you want to make sure that your code is clean before you commit it. It can save you a lot of heartache later. Call to action, this is very important. If a code quality check flags up a problem, like, well, this method has got feature envy in it, the developer might not know what that means. They might not know what they can do about it. They might not have the time to do anything about it. And all of this means that you end up in a situation where people are constantly being bombarded with information about code problems that they're not able to fix for whatever reason, which can be very demoralizing and doesn't really help anybody. So make sure there is a clear call to action. So when I write a tool to check for each feature envy, when it reports feature envy, it should make a suggestion like, maybe you should consider moving this method. Maybe there should even be a link in there in the report to a web resource that explains how to move methods in refactoring without breaking your code. So there has to be a clear call to action. Rising tide. So if you're working on legacy code, which you know is full of issues, you know it's full of crap, it can be quite demoralizing and not especially helpful for someone to come along and say, well, the quality bar should be all the way up here, but your code is all the way down here. Your code is shit. That's not very helpful. You know it's shit. What you can do is set a quality gate such that the bar for quality is set where the code currently is. That is to say, if your longest methods are, say, 200 lines of code, set the bar for method length at 200 lines of code, and if it gets any longer, then you fail the build. Over time, as the code improves, as you refactor the code and make it more useful, and as the water level rises, if you like, for quality, you can move the quality bar. So if, for example, after a few months, the longest method is now 100 lines of code, you can move the bar to 100 lines of code and say, look, if it gets any longer than that, we will fail the build. So gradually the quality improves, and you draw a line in the sand where the quality currently is. Far more helpful than being told your code is shit. So rising tide can be very helpful when working on legacy code or code with technical debt that you know about. And finally, adopting by stealth. I'll mention this very briefly. This is a whole discussion, really. So very briefly, whether it's TDD or refactoring or continuous inspection or any of those technical practices, they have quite a steep learning curve. And therefore, productivity can drop through the floor if you adopt them on real projects. If you try to learn them while you're doing real work, people will notice. Managers will notice. Customers will notice. Other teams will notice. Therefore, don't adopt them. Don't learn them on project time. Now, this is quite contentious. If you're working for an enlightened company like Google, you might get 20% time, and that gives you the bandwidth to try stuff out and to learn stuff and gain confidence in it before you start applying it to real critical projects where time is of the essence. If you don't work for an employer as enlightened as Google, then I'm afraid you're going to have to suck it up. You're going to have to start using your own time. You have to make time to learn this stuff. The reason why is very important. If you learn on project time and the drop in productivity, the learning curve becomes visible, you'll come under enormous pressure. I've seen this so many times. You'll come under enormous pressure to drop that practice, to stop learning. And then quite often it'll become, a dirty word in your organization. So let's say, for example, it was TDD, and you tried TDD on a real project and you hit the learning curve, and the stuff wasn't getting delivered for a while. And then after that, no one's allowed to mention TDD. I've seen that so many times because TDD slows you down. TDD doesn't slow you down. Learning TDD does. And it's the same with continuous inspection. Adopt by stealth. Okay, so what I'm going to do very quickly is just go into this Visual Studio project. So this is an implementation of my feature envy rule. And I just want to highlight some things here. First of all, this is the unit test for my feature envy FX cop rule. And there's a bunch of test cases we've got here, some that I've mentioned and some that I've since thought about or come across. And underneath this, you will see that there is the example code, methods that contain examples of feature envy, methods that don't contain examples of feature envy. And each test case is about a particular example. And I've developed it in a test-driven way. So I've actually fleshed out my implementation of the rule, which you can see here. I fleshed out this implementation one example, one test case at a time, and I put considerable effort into trying to make sure that this code is clean, that it's readable, that it's easy to understand, that each method is only doing one thing, and so on and so forth. So it's very important that this is clean code, that it's approached in a disciplined way. The other thing I want to briefly illustrate is, if we go back to our Solution Explorer in Visual Studio here, don't worry if you're not a Visual Studio user, hopefully it'll all make some kind of sense to you. I can set this up so that when I want to do a code analysis on this solution using, in this case, FX cop, if I run that, you will see, let's just run it there. It'll take a few seconds. Crunch, 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 crunch. Oh, there we go. It has spotted examples of what it thinks are feature envy inside the code for this particular solution. In this case, inside the test. So some of my test code, my implementation of the feature envy rule, FX cop rule, it thinks have feature envy. So let's look at this example here. This first test, methods that make multiple calls to collaborators have feature envy. So I'm reading the code for this method, and I can't see what I would consider to be feature envy. So this is what I was talking about earlier about exploratory testing of these quality checks. This is what I would say is a false positive, and therefore I need to have a look at this code and then go back to my implementation. Basically, this is a new test case. So I would add a test that actually points this test at itself and tests itself to see whether or not it should or shouldn't be feature envy. So there you go. There's the basic idea of continuous inspection. The most important thing to remember is that it is an agile process, it is an iterative process, and it can be a disciplined, test-driven process. And you've got to eat your own dog food here. You've got to apply the care and attention that you want to pay to your own code, your source code, your production code, to the code for actually doing the code quality checks. Right, so that's it. Again, apologies that I'm not with you at CraftConf today. I hope this has given you a flavour. If you've got any questions, I'm just Jason Gorman, all one word, on Twitter. Or if you've got a longer question, I'm jason.gorman@codemanship.com. Thank you very much and enjoy the rest of the conference.